Okay, this video is going to be about the ideal gas law. So in the previous video, when we went through other gas laws, we looked at Boyle's law, Charles' law, and Avogadro's law. And we saw from Boyle's law that the volume of a gas of a certain fixed mass was inversely proportional to its pressure. So if we said if its pressure doubled, then the volume would have halved. Then we looked at Charles' law and saw that the volume of a gas was proportional to its temperature. So if we increase the temperature, the volume would also increase. Then Avogadro's law, this is the law where we saw that the volume is proportional to the number of moles of the gas. And we saw that the volume of 1 mole at standard temperature and pressure was 22.4 litres, where if it was at room temperature, it was 24 litres. So these all together then give us this little line. The volume is inversely proportional to 1 over the pressure, proportional to temperature, and proportional to the number of moles. From that, we can write this equation here. Now, R is the constant. The constant brings us from a proportionality to a formula. R here is the universal gas constant. Now, if we just rearrange that equation there, if we bring the pressure, the P, from under the line and bring it over to this side, it becomes PV equals nRT. And this is the equation that we're going to be dealing with today. It's called the ideal gas equation. Okay, to use this equation, our pressure must be in the unit of pascals, which we know to be the Newton meters squared. Our volume must be in meters cubed because our pressure is in meters as well. So we need to keep the same units. It can't be in centimeters cubed and it can't be in liters. So it needs to be in meters cubed. Our temperature has to be in Kelvin. And then our constant is this number here, 8.31 joules, mole to the minus 1, Kelvin to the minus 1. Okay, so for the conversions for meters cubed, I just want you to remember that 1 meter cubed is 1,000 litres. So if I just want you to keep that in your head there for all of our conversions in the future when using this equation, this formula. So I'm going to write in the first question here. Okay, so here's a question. Calculate the volume that 20 grams of oxygen gas will occupy at 25 degrees Celsius and 20 kilopascals. So oxygen gas, it is O2. Okay, so you'll need to know that oxygen gas is O2. Okay, so what do I know? What can I work out? I know 20 grams of oxygen. If I have the mass of a substance, I can work out how many moles there are of that substance as well. That formula is mass over relative molecular mass, and that gives you the number of moles. So I have the mass, and then the relative molecular mass is 2 times 16, which is 32. And 20 over 32 gives you 0.625 moles of oxygen present in the amount of gas that we have. So now let's look at what else we have. So that would be our N. That's the number of moles that we have. We also have the temperature, which is 25 degrees Celsius, which we can convert to Kelvin, which is 298 Kelvin. Then we also have the pressure, which is 20 kilopascals. So just change that K to kilos, is by 10 to the 3 pascals. And you can write that as 2 by 10 to the 4 either, that's no problem. And our constant always stays the same, 8.31. And that's in your log tables. Okay, so let's look at our equation. Do I have everything first of all? Do I have the pressure? Yes. Do I have the volume? No, that's what is being asked of me in the question. Calculate the volume. Do I have the number of moles? Yes. The gas constant? Yes. The temperature? Yes. So we're just going to fill it all in. And that's it filled in. You can just see we volume is the only one that's missing there. And if I multiply all of the right hand side out into the calculator, I'm going to get this number. And then volume divided by the 20 by 10 to the 3. So I've just brought that 20 by 10 to the 3 across the equal sign and divided it in. And I should get my volume to be 0.7738. And remember that the pressure is in meters, so the volume here is also going to be meters cubed. Okay, so if you want to change that to liters, this is your conversion. 1 meter cubed is 1,000 liters. So if you multiply this side by 0.77 and do the exact same to the 1,000 times 0.7738, so you're multiplying both sides of the conversion by 0.7738, you'll get 77.38 liters. And that is your volume of the gas. Okay, so I'm going to write out the next question for you. Once you see it pop on the screen, I'm going to talk through it, and then you can pause and give it a go yourselves. Okay, so here's the question. I've written out all of the important parts of the figures that were in the question. We have a canister full of chloroform. We have the mass, the volume, the temperature, and the pressure of the gas. What we need to figure out is the relative molecular mass of the gas. So see what you can do with those figures. Okay, so I'm going to rewrite them out. So our formula is this. Now pressure, 100.5 kilopascals. That needs to be converted just into pascals or Newton meters squared. You do that by just converting the K to by 10 to the 3, and that's pascals or Newton meters, like that. Okay, the volume is 127 centimeters cubed. Okay, so remember the conversion, 1,000 liters is 1 meters cubed. So 1 liter would be 1 over 1,000. Literally just dividing both sides by 1,000 there. 1,000 divided by 1,000 is 1. And there we go. Now, if I just wanted to quickly convert centimeters cubed into liters, it's 0.127 liters. So, multiply both sides by 0.127. 1 times 0.127 is 0.127. and we're going to get 0.127 over 1,000 here. And then for the final answer here on this side, we're going to get 0.000127 meters cubed, which is going to be 127 by 10 to the minus 6 meters cubed. So that's how you're going to convert from 127 centimeters cubed to liters to meters cubed. You might have a different way, an easier way of doing that. That's just the way I like to do it. And using this conversion really helps, and to remember that. Okay. Okay, so the pressure is done, volume's done. What else do we have? We have the temperature, which is 98 degrees. We need to add the 273 to convert to Kelvin. We've got 371 Kelvin there. The R, the constant, is 8.31. And we just don't have N. But everything else is now converted into the right unit. So we can fill in our formula. Pressure and that's it filled in. Just going to rearrange it then so that N is on its own. Bringing those two for the right hand side over. And if we put that all in the calculator, we're going to get a long number. Moles of the chloroform. Okay, I'm just not going to round it quite just yet, because I'm not at the end of the question. There's no problem leaving the long numbers there, it's fine. So we need to get, we have the mass, so we've used this, we've used this, we've used this. We need to get the relative molecular mass, and I actually have the mass of the substance. So this formula, number of moles equals the mass over the relative molecular mass. Okay, and I need to find the relative molecular mass, so I need to get that on its own. So I can fill in what I have. I have this amount of moles. The mass is 0.495. And the relative molecular mass, I don't know. So, with a bit of rearranging, you should get the relative molecular mass to be around 119.56. Closest whole number then would be 120 grams. And that's that question done. So the next question that I'm going to do is actually an exam question from 2022, question 10A. You should be well able to do this one now, so I definitely recommend you pausing it the minute you see it all fully written out in front of you and giving it a go. Okay, here's the question, so you can pause now. Okay, so when you're doing these, you have to underline the important sections and to the nearest whole number, the relative molecular mass. So we've already done this type of question, so you should have been able to bring it down to about 80% at least. And if you want, you can look through this, my solution, go back and try and finish it off yourself again. So we're going to write out everything. 4.85 grams. Volume is 60 litres. Pressure, 99 kilopascals. Temperature, 22 degrees Celsius. And I'm doing that, writing them all out just to convert. So, remember my conversion was 1,000 litres is a 1 metre cubed. So that means that 1 litre would be 1/1000 meters cubed, which means 60 litres would be 60/1000 meters cubed. And 60 litres is 0.06 meters cubed. So that's that conversion done there. Then 99 by 10 to the 3 pascals, or our Newton/meters squared either. So I'm going to write in the Newton/meters squared just instead. I think that just reaffirms why you need the volume in meters as well, rather than saying pascals, but pascals is the exact same unit. Then the 22 needs to be changed to Kelvin. Okay, so the conversions are done. We can now use our formula. R, of course, is 8.31. Okay, so if we work out the left-hand side this time, we're going to get 5,940 equals N, and then 8.31 times 295 is 2451.45. With a bit of rearranging there, we're going to get N to be 2.423 moles of the gas. Okay, so now go back to our number of moles equals the mass over the relative molecular mass, and it's the relative molecular mass we want to get. The mass was 4.85. Now with a bit of rearranging there, you're going to get the relative molecular mass to be 2 grams, and that's rounded to the nearest whole number. So it's not a bad question. Nice and easy once you've done your conversions. The most important thing is making sure that these conversions are done properly and that they're all in meters. Okay, that's it.